And now that I've got the recorder going, I'm going to share my screen with you all. And you might ask why I say this every time we meet, but it literally, I'm saying it so that I don't forget to do it. On in this whole process, when I was first learning how this worked, I would forget to turn on the recorder or forget to share my screen or just silly things like that. So I'm walking myself through the process. Matt, you had some questions. And how about Matt Davis?
Yes, sir.
What were your questions?
May you please work out number 21?
21, 3 radical 18. So to start with, 3 radical 18 needs to be simplified. You can pull out a 9. And that's going to be 3 times 3 times the square root of 2. So that's going to be 9 square root of 2. That's the first thing. And then 2 over 25. Square root of 2 over, whoops, 25. All right, so we've got, that's going to be radical 2 over radical 25, which is radical 2 over 5, which technically is, we could also look at this as 1/5. I don't know if you guys look at it that way, but 1/5 times the square root of 2. And that being the case, that those two terms are now like terms. Remember, what does it take to add and subtract radicals? You got to have the same root and the same radicand, in which case you would just add their coefficients together. So 9 plus 1/5 would be 46/5. So we got 46/5 square root of 2. And that would be how we would combine them. Again, remembering that in algebra, we prefer improper fractions as opposed to mixed numbers and decimals. So like 9.2 would be the decimal approximation, or the decimal version of that, 9.2 radical 2, but we would prefer the improper fraction.
And you got that because, I guess, never mind, I see it. Thank you.
Okay, what else?
I have a question.
Okay.
Where did you get the 46 from?
I think that's what Matt was going to ask, and then he said he got it. So let's test him. Matt, where did that 46 radical 5 or 46 over 5 come from?
Because when you add a fraction to a whole number, you have to make sure they have the same denominator. So I put 45.
Oh, now I get it.
Yep.
And can we work out number 30?
Yes. All right. Anthony, did you have a question on that first one?
Oh, I was gonna ask it on number 30 also.
Oh, perfect. All right, let's look at 30. 3 and then square root of 5/12. Square root of 12/5. Look at them getting cute with the reciprocals there. Minus 1/3 radical 60. All right, so we can just start pulling these apart. Okay, just take one piece at a time. So we got a coefficient of 3. We got radical 5 over radical 12. Now my goal for you guys, and this might be a lofty goal, okay, but I would really like it, excuse me, if you could go ahead and simplify square root of 12 in your head, get 2 radical 3. Okay, that's my goal, to be able to, for you guys to be able to do that. So 3 times square root of 5 over 2 radical 3 would be superb. Okay, and then when we rationalize that, and I'll put that in red, when we multiply by square root of 3 over square root of 3, okay, then that becomes square root of 15 up at the top, and then that becomes, don't forget we had a 3 out front, that becomes 2 times 3 down at the bottom, because radical 3 times radical 3 just becomes 3, right? So the 3's would cancel out. Okay, and that's that first term right there, simplifying everything down to where that's, if you wanted to look at it as a coefficient, you could say that's 1/2 square root of 15. Okay, so take a moment, read through that, kind of see how that worked, and then you tell me, and I'm just going to call on some random folks there. I'll start with Nick. Nick, you tell me, how do I rationalize this middle one, given that it's 2 square root of 3 over square root of 5, like we talked about a moment ago. They're getting cute with the reciprocals there.
I don't know how to do that. That's what I was going to ask next.
All right,
I
so
was confused about that.
when you guys see a basic radical in the denominator, like square root of 5, I mean, for Pete's sake, rationalizing these denominators would have been like Chinese, learning Mandarin Chinese, if you didn't understand the basic examples. So like, let's go back to those basic examples. And actually, yeah. This would be a good note to have down if you didn't write it already. When we're getting a square root out of the denominator, it is by multiplying by a clever form of 1. And in that clever form of 1, we choose such that when we multiply, it gets rid of the radical. So like, look at this example. This was a real basic example we did last week, right? To where we said, okay, I'm going to multiply by a clever form of 1 such that, that's radical 3 over radical 3, such that when I multiply these two, I get the square root of 9, which is no longer an irrational number. That's where my new denominator is 3, is because we multiplied by something to cancel that radical out. So Nick, I'll throw it back to you. What could you multiply on this example to get that square root of 5 to become square root of a perfect square?
Square root of 5 over the square root of 5.
Precisely. Very good. So square root of 5 over square root of 5. And then when we group those two denominators together, that would become square root of 25, or we would just simply say just 5, whereas the top is 2 square root of 15. And again, if we wanted to write that up as a coefficient, it would just be 2/5 square root of 15. So I'm already thinking ahead. I'm already like, I bet we could put these two terms together. And in fact, this last one's going to be similarly, because we could pull out a 4, and we could just say, all right, well, that's square root of 4 times square root of 15, which is 2 square root of 15, and 2 times a third is just 2/3. That's where we got our 2/3 square root of 15. So do you guys notice how all three of these are the same radical term? All three of these have square root of 15, square root of 15, square root of 15. So what do? I just add their coefficients. Okay, so this looks like it's going to be 3/5 plus 2/3 times the square root of 15. It's almost as though you could treat this like a variable. Like if I had 1/2 x plus 2/5 x plus 2/3 x, you're going to have yada, 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 whatever that is, times x. Well, we're treating square root of 15 like that, okay? So you can make a note. I can treat radicals like variables in that sense. And the only question is now, how do I combine these two fractions and get an LCD of 15 as it would be? So it looks like 19 15ths. Is that what you guys got?
Yes.
Square root of 15. If I'm counting in my head right, change both of those fractions like Jack asked about on the last example. Multiply by 3 over 3, multiply by 5 over 5. You get 10 and 9, so that's 19 15ths. All right, other questions? Anthony, I think you were trying to say something and maybe your mic cut out.
Oh, I said I had a question on number 30.
Oh, okay, that's the one we just did, right?
Yeah.
All right, perfect. Who else? Anybody else on the homework?
36.
36. All right. Getting into the C-level problem now, I think. That's good. So 36 says, all right, so we got square root of, and then x squared, x squared over 49 minus x squared over 121. Assume that variables represent positive real numbers, and we want to simplify. All right, so again, I haven't worked this one out, so I'm going to play with this one kind of like I would suggest you guys do, where you just, quote, try something, And I look at these two fractions. What do I notice about x squared over 49 or x squared over 121? What do you guys notice about those two fractions?
They're both perfect squares. Like if 49 is 7 and 121 is 11.
Perfect. That's a great observation. So first things first, when we try things, I'm going to try to factor them out because I notice, hey, look, there's a perfect square. There's a perfect square. And then what's in the middle between the two of them?
And modifying.
Subtraction.
Yeah, so that's the difference of two squares. That would be like saying a squared minus b squared. And that factors out as a plus b times a minus b. So this is a little throwback question to chapter 5 when you guys learned about factoring the difference of two squares. So this is going to become, and I don't know if this will work or not, honestly, I'm just trying something, but this will become a product. Okay. Now I happen to know from recent experience that you guys, we've all been talking about how you could take the radical of a product and you could cut it up and make it radical times radical. So this is sort of the outline of my thinking on this problem. And I haven't worked this problem in at least 12 months, maybe longer. So I don't know. This might work, it might not. But in this case, let's try and factor it out. What do we got? X over 7 plus x over 11, and then x over 7 minus x over 11. Does that look good to you guys as far as factoring out the difference of two squares?
Yes.
All right, Thomas, how can I check to make sure that I factored that properly? Just in the middle of the problem, it's homework, I got plenty of time on my hands. How can I make sure I didn't screw that up?
Foil it back out.
Absolutely. And fellas, when y'all are doing homework, be diligent enough to do that exactly. To say, okay, I'm gonna foil this out and see if I've messed it up. Now, once you've split, great divide right here. Okay, once you've split up the two radicals, here, what do we got? X over 7 plus x over 11. X over 7 minus x over 11. Now I'm thinking, okay, let's combine like terms. Let's get a common denominator. This is one of the reasons why this is in that section. Let's multiply this one by 11 over 11. Let's multiply this one by 7 over 7, and then similarly on the other factor, 11 over 11, 7 over 7, so that we can get our common denominators. So this is going to become 11x plus 7x all over 77. And that second one's going to become 11x minus 7x all over 77. Again, because we get a common denominator there, and we can easily combine those fractions. Scoot these two guys close together. So I'm gonna pause real quick, make sure everybody's cool on that. What we did was we just multiplied by a clever form of 1 in orange, got a common denominator, and then put those two fractions together. Okay. Now, what do I notice? I notice that I'm multiplying a couple of things. So I'm going to split them back up now. Radical 77. 11x minus 7x over radical 77. So I can take the radical of the top and the bottom. That's a basic radical rule, right? Remember how we said if you've got the square root of a over b, that's just square root of a over square root of b. Earlier, we had made use of a similar rule where it was the square root of ab being the square root of a times the square root of b. So do you guys see how, like in this C-level problem, look at the little in red, look at those background things that they're asking us. I'm lagging, I know, sorry. Look at those things that they're asking us to remember, to recall to mind, all the stuff all the time, right? That's that ASAT that we talked about last week. Okay. I got to know all the stuff all the time and be able to use it. Now, back to this example. So we're multiplying. So the bottom is just going to become, I don't know. Stephen, what do you think the bottom is going to become? Hudson, you with us?
Yes, sir. My mic was muted. I'm just thinking.
Okay. What's square root of 77 times square root of 77?
The square root of 77 times the square root of 77 is the square root of 5929.
I have no idea what the square root of 5929 is outside of the context of this, but I do know that when I multiply a radical times itself, the square root goes away.
Yeah.
You know what I'm saying? So like, what's square root of 77 times square root of 77? Ah, that's 77. just like in the last examples, and again, this is why they have this in this section, when we look right here, when we multiplied and we said, hey, what's the square root of 3 times the square root of 3? Ah, that's 3. Or we said, oh, what's the square root of 5 times the square root of 5? Ah, that's 5. You know what I'm saying? So like the whole idea is that when we multiply a square root times itself, it goes away. Now in this case, it just so happens that the way that we worked through this problem, it sort of rationalized it for us. But when we say square root of 77 times square root of 77, our denominator is going to turn into a nice, neat 77. Okay, now I really want you guys to stretch here with me. Look at the numerator. We're multiplying a square root times a square root. Now, these are not the exact same radicands, so the square roots are not going to go away. So I am going to have a big fat square root, and I'm going to need to multiply their radicands. But these two radicands are conjugates of one another. In other words, I don't really have to FOIL them out. Cullen, do you remember that when we multiply conjugates, the FOIL isn't all necessary? Cullen, what's the only 2 letters that are necessary?
The F and the L.
Yeah, the outer cancel each other out with the inner, and we're left with the F and the L. So if I multiplied, for example, if I multiplied the first times the first, right, that's going to be 121x squared. And if I multiplied the last times the last, 7x and negative 7x, that's going to be minus 49x squared. And perhaps that will be good enough for me. I guess, like, technically, we could have left it factored out. You know what I'm saying? So, like, we could have had big fat square root and then binomial times its conjugate up top and 77 down at the bottom, and that would have been okay. What's that going to be? 11x plus and minus 7x. Like, we could have left it that way, and I guess that's okay. But I went ahead and multiplied it out just for kicks and giggles, I suppose. Okay, but what was the main instruction for this problem? Did you guys notice that? What was the instruction that they told us? Who's got their book? Read the one word at the very beginning of the instructions.
Simplify.
It says simplify. So to simplify a radical expression in this context means to get the square root out of the denominator. Okay. And in this case, we had a sort of a roundabout way of doing it, but eventually the square root of 77 times the square root of 77 multiplied itself out. And there might have been another way to work this problem. I don't know. Like I said, just kind of shooting from the hip here. This is what struck me. But do y'all have any questions on how that worked?
Could you have simplified the numerator? Because I got 6x square root of 2 over 77.
6x square root of 2.
I added 11x and 7x and got 18x, and 11x minus 7x and got 4x.
Oh, look at you being smarty. I'm so stupid. Look at that. Look at that. Look at that. Yeah. Was that Robert? Robert, that's awesome, man. Great observation. These two guys come together. Duh. Okay, they're both x terms. And so the 77x, let me just squeeze this in here. So this would be 77x. And then what's 11 minus 7? 4. This is 4x. And so good. Not 77. Ugh, I'm losing my brain today, boys. It's been a long day. 18. And I think you said that too, Robert. 18x and 4x. And what's 18 times 4? Is that 72?
Yes.
All right, so let's write that up. So 72. Oh, I like that even better. Hey, you know what? Let's bonk this. Because if you go this route, Robert, that you're mentioning, so make sure I don't screw this up now. 11 and 7 is 18. 11 minus 7 is 4. 18 times 4 is 4 times 8. 4 times 8 is 32, and 40 is 72. Okay, good. So we got 72x squared And that's under our square root. So we definitely need to simplify that more. Good night, America. 72 is 36 times 2. So that's 6. X squared is going to be x. And I wonder if we need the absolute value. Let's look back through the problem. Originally, it was x squared, so there were no guarantees that x was non-negative. They say, in the instructions, they say assume that all variables represent positive real numbers. So we don't need absolute value. So we got, what is that? 6x square root of 2 over 77. Yay for Robert. Real good observation there. So you know what? And that's a good illustration, fellas, of number one, don't be too hasty in writing up your answer just in whatever form you ended with, because, you know, I guess I could have, I might have been tempted just to stop right there and say, well, I don't need to factor it out and do anything else. But when we did factor it out, then we noticed, as Robert did, or at least Robert noticed, that these two terms could come together. And I suppose we could have done that right here. Wouldn't we have gotten 72x squared? Yeah. So in either case, we don't want to stop until we're finished. And in this case, we definitely simplify it out further. So Robert, kudos to you on that one. And you know, that's a good example of a problem. I mean, you and I've been sitting here working it together for 10 minutes. You should sit down and think about a problem like that for half an hour, maybe, you know, and chew on it and think about it and go eat some supper and come back. Y'all are getting to the point where not every one of your math problems is going to be workable in just the drop of a hat, where you just sit down and knock it out. You know what I'm saying? Like next year, Mr. Perry or whoever you have, you know, we'll give you, in geometry, you'll get proofs. And man, those are like long, like take a whole page to write up type problems that you might have to think about, you might have to consider. So anyway, I like this problem to end with. And what I'm going to ask you guys to do for me, I've got a little, not like super big homework, but I do have a little bit of reading for you. We're going to start section 1110. Okay. Now, section 1110 is on, let me see if I can get there on my book, on page 547. Okay, 547. And I'm going to give you like a little step-by-step process. Okay. So what I want you guys to do, I don't want you to take time to write this down right now, but tomorrow when we have our class, we're going to be going through this process, going to be going through this step-by-step process. So if you just kind of look ahead at section 1110, maybe read through a couple of the examples and consider what you would put together as a process, and then we'll see if yours matches up with mine that I've got right here on the screen. And like I said, we'll go through and work this lesson tomorrow. Okay. Y'all got any questions for me before we dismiss?
No, sir.
All right, then. I hope you guys have a great afternoon. The weather still looks great outside, so get out and go fishing, okay?
Go fishing. Okay?
Yes, sir.
Live Jesus in our hearts.
Sure.
Live Jesus in our heart.
Forever.
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 Thank you.
Thank you, Mr. Morgan.
You bet.